Welcome back to Learning as a Hobby, everybody. In this video, I'm going to try and finish up the exercises in Michael Spivak's book Calculus, 4th edition, for Chapter 2. So I've been on Chapter 2 for quite a bit. I'm ready to move on to Chapter 3. In this video, I'm going to almost finish up all the exercises for Chapter 2, with the exception of two problems. I'm going to skip 21 and 20. Was it 21 and 22, I think, for now, because I haven't had a chance to finish those up yet. And I'm going to actually try something a little bit different with the way that I present the material here today. I'll explain that in a minute, but I think what I'm going to do is, because I have a lot of stuff to do today, I'm going to put off I'm just going to get through the problems that I've finished, and I'm going to put off problem 21 and 22. I'll just tack that on to the front of the exercises for chapter 3 when I get to them, because I want to move on to chapter 3. So, and there's a couple other videos I wanted to post today, and I have a bunch of other stuff to do today. So let's let's just work with what we have. So the way I want to do this a little bit differently, because so these problem videos, or at least the last one for Spivak, has these videos tend to run a bit long. So I think what I want to try to do, let me share my screen here, is maybe write them up beforehand, which is what I actually did for this video. This way I don't, because a lot of time in the videos that I've posted so far has been wasted just writing stuff on the board. So I think if I write up the problems and the solutions first, I can save a little bit of time of having to do that, and I can just explain my solutions. So that's the way that I'm going to do it in this video today. Let me know if anyone's watching this, let me know if you prefer to see the videos this way, or if you prefer to see them done live, if you have a preference. But I just think that the videos might, be a little bit shorter if I don't have to worry about writing everything on the board. So that's what I'm going to do. And if you remember, for the problem set for chapter 2, I did part 1 for that already, and we ended that one, I think, with question number 6. So I'm going to start here with question number 7, which in the book he says use the method of problem 6 to solve this one. So that's what I'm going to do here. You also need this useful fact that I have written down. You have to use the binomial theorem, which is where this formula comes from, which is why I wanted to prove the binomial theorem in that last video as well. So with using the method from problem 6 and the binomial theorem, we can solve this problem. So the problem says, use the method of problem 6 to show that the sum of the first n p powers of the integers, so like 1 to the p, 2 plus 2 to the p plus 3 to the p, etc., can always be written in the form that he has below. So n to the p plus 1 over p plus 1 plus, and then polynomial terms of degree less than p plus 1. So that's what we're going to show. We'll do it by induction. A lot of the problems in this chapter are done with induction. So all right, so if we induct on the power p, the base step is p equals 1. And we already know that works, because one of the things that we proved was this formula. I think we did that actually in the chapter itself. So the sum of the first the sum of the first n natural numbers is given by this formula, n times n plus 1 over 2. And if you distribute, you get n squared plus n squared plus n over 2, which is the same thing as n squared over 2 plus n over 2. So that formula that he has here is satisfied for the p equals 1 case. All right, and then using that method from problem 6 to derive the formula for the general expression, and using this fact here, we get 2 to the p plus 1 minus 1 to the p plus 1 is given by this, and so on. And if you add all those things together, notice that the middle terms all cancel out, and you're only left with n plus 1 to the p plus 1 minus 1. And on the right-hand side, for each of the like terms, notice you get p plus 1, choose 1, and then 1 to the p plus 2 to the p plus n to the p, etc. That's the sum of the first np powers of the integers. And down the line, you just add everything up. So here you get the sum of the first np minus 1 powers, and all the way down to these, these expressions here. 1 added to itself n times is just n. Okay, so for that formula, if we use the inductive step here, I'm just using I made up the shorthand notation just because it's kind of unwieldy to write here. So the sum let's assume that the sum of the first j power n, how do I say this? The sum k going from 1 to n of k to the j power, where j is the degree of sorry, it's equal to polynomial p sub j, where the degree of pj is less than p plus 1. So in other words, that let's assume that this sum is some polynomial of degree less than p plus 1, all right, for all j between 1 and p plus 1. All right, that implies that from this formula here, that implies that if you solve for this expression, so in other words, you bring all these things over to the other side and divide by p plus 1, choose 1. All of these lower order expressions here, lower degree expressions here, can be written in terms of polynomials of degree less than p plus 1. So I'm just writing that here as a sum. So you could solve for kp in terms of things that look like this. And if you calculate what the leading term is, it would be n to the p plus 1, just from the binomial theorem, right? It would be n to the p plus 1. Divided by this expression here, 1 over p plus 1, choose 1, which when you simplify gives you 1 over p plus 1. All right, so that shows that this thing here can always be written in that form. All right, so that follows by mathematical induction. All right, question number 8 says prove that every natural number is either even or odd. And again, we'll do this by induction. So if we induct on n, the base step is, let's do 1 and 2. So 1 is odd, obviously, because it's 2 times 0 plus 1. So it has the form of an odd number. And 2 is even because it has the form of an even number. In other words, it's 2. Whoops, that should not be 0. That's a typo. That should be 2 is 2 times 1. Obviously, right? So that's even. Okay. And then if we go on to the inductive step, assume there exists a natural number k such that, so I broke it up into 2 cases. So let's assume that if k is even, then that means that k is 2m for some natural number m. And that means that k plus 1 is 2m plus 1. And that means that k plus 1 has the form of an odd number. And the second case is if k is odd, then k is 2m plus 1 for some natural number m. Then k plus 1 is 2m plus 1 plus 1, which is the same thing as 2m plus 2, which is 2 times m plus 1. And m plus 1 is a natural number, so that means that k plus 1 is even. All right, so that follows by induction. Okay, number 10 says that the well-ordering property implies the principle of mathematical induction. This is the converse of one of the theorems that we proved in the textbook, if you look at the notes for that section. Okay, so again, this is by induction. So here, assume that the hypothesis is that the well-ordering property holds for the natural numbers. So assume that the well-ordering property holds for the natural numbers. And then some definitions here. Let A be a non-empty subset of n, such that 1 is an element of A and k is an element of A implies that k plus 1 is an element of A. Those are the 2 parts for principle of mathematical induction, if you remember, which is what we're trying to show follows from the well-ordering principle. Okay, and then we define a set B to be the subset of natural numbers that are not in A. If A is not the entire set of natural numbers, then B is not empty. And by the well-ordering principle, that means that B has a least element n. Okay, so if we go here to the base step, that n can't be one equal to 1. By n here, I'm referring to the least element of the set B. So n can't be equal to 1 since 1 is an element of A. And the way that we define B was that it's a subset of natural numbers that are not in A. All right, so the base step is satisfied. The inductive step says since n is greater than 1 and n is the least element of B, then n minus 1, first of all, is positive natural number. Well, all the natural numbers are positive, but it's, it is a natural number, in other words. Also, n minus 1 is an element of A because n is the smallest natural number that's not in A, right? So that means that n minus 1 is an A. But by the way that we define the set A, that means that n is also an A, and that contradicts the fact that n is an element of B. Therefore, B has to be empty, and A has to be the entire set of natural numbers. So that shows that the principle of mathematical induction holds. Right? And that, again, that's just a proof by induction. Then we have a similar type of thing here but now we want to prove that the principle of mathematical induction implies complete induction. And he does give you a hint in the book, which I have written here, so you guys have access to it as well. If A contains 1 and A contains n plus 1, whenever it contains 1 through n, consider the set B of all k such that 1 through k are all in A. Okay, so I use that fact here. So proof, again, it's by induction. So the base step says the base step says 1 is an element of B, since 1 is an element of the set A. I'm defining A and B to be the way that he defines them in the hint here. All right, then the inductive step, if 1 through k is an element of A for some natural number k, then by the way we define A, then k plus 1 is an element of A, and that implies that 1 through k and then k plus 1 are all elements of B, and therefore B is the entire set of natural numbers by principle of mathematical induction, and that means that complete induction holds. Okay. All right, so that was number 11. I feel like I'm going through these a lot faster than when I write them down, which is one of the things I'm a little bit worried about, that it might be confusing doing it this way. So again, let me know in the comments if you prefer it this way, or if you prefer to see me actually, working through the problems in real time. Whichever is the most instructive, I guess, would be best. Okay, 17 part A says if n is a natural number and n is greater than 1, then n is a prime or a product of primes. Okay, so they want us to prove that. Again, unsurprisingly, it's a proof by induction. So base step 2 is a prime number, so that checks out. Inductive step, suppose the property is true for 1 through k for some natural number k, where k is greater than 1. Okay, because if you remember, we don't define 1 to be a prime. The first prime is 2. Okay, so if k plus 1 is prime, then we're done. So we can start by assuming that k is composite, meaning that it's not prime. Okay, then that means that there exists two natural numbers, a and b, that are greater than 1 and less than k plus 1, such that k plus 1 is a times b. And since a and b are both less than or equal to k, that means that a and b are products of primes or primes themselves. Therefore, k plus 1 is a product of primes. Okay, so that shows that for every natural number is a prime or a product of primes. Okay, part B says, using this fact, prove that the square root of n is irrational unless n is a square, so n equals m squared for some natural number m. And this proof is very similar to the proof that we did in the book about showing that square root of 2 is irrational. We're just doing this in general now in this case. All right, so the proof says, assume that n is not a square of another natural number for any m and n, and assume that the square root of n is rational, so it's k over t, where n is in square root, that should be the square root of n is in reduced form. So k, in other words, k and t have no common factors. Then n, if you square both sides of square root n equals kt, you get n is equal to k squared over t squared. And if you bring t squared over to the left-hand side, you get t squared n is k squared. And since n is not m squared for any natural number m, that means that there exists a prime p such that p divides n. Okay, that means that n is p times s for some other natural number s. So t squared n is ps t squared, and that's equal to k squared from above, which means that p divides k squared, which means that p divides k. I don't think we proved that theorem in this book, but it is a theorem from number theory. A prime divides, if you have a prime dividing a product, let's say a times b, then the prime p has to divide one of the factors. So it either divides a or it divides b. Here, k squared is k times k, so that means that p has to divide k. All right, and that contradicts the fact that k over t is in reduced form, so that shows that the theorem holds, or the proposition holds. All right, so the square root of n is irrational unless n is m squared. Okay, and then in part C, they want us to prove more generally that the kth root of n is irrational unless n is a perfect kth power of a natural number. I skipped that part because it's virtually identical to what we just did, just with a higher power. So I skipped that part and went on to part D. Prove that there are an infinite number of primes. And this is done by a proof by contradiction, as opposed to induction. All right, so assume for the sake of contradiction, there are a finite number of primes. I should say also, this is a famous proof too. This is due to Euclid, I think. And it's one of this proof you see a lot in like proof classes, like when you're learning proofs, because it's such a famous proof. Same thing with the proof that square root 2 is irrational. Anyway, assume for the sake of contradiction, there are a finite number of primes. So say the primes are p1 up to pn, and consider the product, the number n, which is defined to be the product of all those primes plus 1. Right? Since n is greater than pj for all j1 through n, that means that n is not prime, because we said there were only a finite number of primes, right? p1 through pn. So it can't be prime. That means it has to be composite. But if n is composite, that means that it's divisible by one of the primes, and clearly that's not, because when you divide by any of the primes, you get a remainder of 1, right? Therefore, that's our contradiction, so that means that there are an infinite number of primes. Okay, number 19. I don't think he asked us to prove this in the book, but I wanted to do it just because it's a famous inequality. So, so they want us to prove Bernoulli's inequality, which is stated below. If h is greater than -1, then 1 plus h to the nth power is greater than or equal to 1 plus nh for any natural number n. And then he wants us to say why it's trivial if h is greater than 0. All right, so the proof of Bernoulli's theorem is, again, induction. So if we do a proof by induction, induct on the power n, then 1 plus h to the first power is the same thing as 1 plus h, which is the same thing as 1 plus 1 times h, so that checks out. The inductive step is next. So assume that 1 plus h to the nth power is greater than or equal to 1 plus nh for some natural number n. And then if we consider 1 plus h to the n plus 1, that equals 1 plus h times 1 plus h to the n, which is greater than 1 plus h times 1 plus nh by the inductive hypothesis. And if you distribute, you get 1 plus nh plus h plus nh squared. And since nh squared is a positive number, right, because h squared is always positive, then that's always greater than 1 plus nh plus h. So you just leave off the nh squared term. And that's, if you factor out the h from the two last terms, you get 1 plus n plus 1 times h, which is the statement of Bernoulli's theorem. So, the form in Bernoulli's inequality. So that shows that it's true for all natural number powers. And then the reason that it's trivial is when h is 0 is because the binomial theorem, if you expand this power using, whoops, where is it? If you expand this power using the binomial theorem, you'll see that all the terms are positive if h is positive. Okay, so that's why. All right, number 20 is on the Fibonacci numbers. It's a theorem about the Fibonacci numbers. If you don't know what the Fibonacci numbers they satisfy this recursive relation. F1 is 1, F2 is 1, and then to get the next Fibonacci number, you add the two previous terms together. So for example, F3 would be 1 plus 1, which is 2. F4 would be 2 plus 1, which is 3, and so on like that. Those are called the Fibonacci. That's called the Fibonacci sequence. And there is believe it or not, a closed form formula for the nth Fibonacci number, which looks like this. Again, this is another thing famous proof that you would look at in like a proof class or something. So again, it's done by induction. The base step, you have to actually go too deep here because the recursive formula has the first two has the end step defined in terms of the previous two. So for the base step, you got to go too deep. So when n is 1, you get the second actually Fibonacci number, which is 1, and for n equals 2, you get the third Fibonacci number 2, and then for the inductive step, if you look at I ran out of space here in the notes, so I should have probably stated the inductive hypothesis here, but the inductive hypothesis is that this number is fn minus 1 and this number is fn minus 2. Right, so if you add those two things together and rearrange some things, you get this. If you notice, this expression here is 1 plus root 5 over 2 squared. This is 1 minus root 5 over 2 squared. And actually let me just, whoops, in order to, let me make sure that the second thing that I'm showing here is shared. I had to continue this on another Jamboard, which is what I was using to write these things down. So continued, you get this, and then when you simplify these two things, you get 1 plus root 5 over 2 to the n, and so on. And that's the nth Fibonacci number. So that shows that it follows from mathematical induction. All right, and if you remember, I said I skipped 21 and 22, but I'm going to try and tack those on to the beginning of the exercises for chapter 3 later on. So, but I did do number 23. Actually, I did a couple more. I did 23 and I did number 5. I wanted to do also just because this formula is famous for, proving the formula for convergence of a geometric series. So I did want to do that just because if he ends up talking about that later on in the book, at least we have it already proved, so we won't have to go backwards. So I'll go through these two problems here, and then I'll end the video. So in 23, he says, the following is a recursive definition for the nth power of a. So you can define a to the first power to just be a, and a to the n plus 1 to be a times a to the n. And he wants us to prove these two properties of exponents using induction. So we want to prove that a to the n plus m is a to the n times a to the m, which you probably remember from your algebra class whenever it was that you took that. And then also we want to prove that a to the n raised to the mth power is a to the n times m power. Okay, and again, it's by induction. So to prove the first property, a to the n plus m equals a to the n times a to the m. Our base step is a to the 1 plus m. That's equal to a multiplied by itself, m plus 1 times, which is the same thing as a. And then you could just move the parentheses by associativity times a times itself m times, which is the same thing as a times a to the m. So that checks out. The inductive step is to assume that, the inductive hypothesis is that we assume that a to the k plus m is a to the k times a to the m for some natural number k. And then we consider a to the k plus 1 plus m, just rearranging the power there. That's the same thing as a to the 1 plus k plus m. And definition of the power, that's a multiplied by itself, k plus 1 plus m times. And then you could rearrange things by associativity. That's a times, in parentheses, a times itself, k plus m times, which gives you this expression here, a times a to the k plus m. And then by the inductive hypothesis, that's a times a to the k plus m, which is a times a to the k when you move the parentheses by associativity, and that's a to the k plus 1 times a to the m, and that shows that it holds. And similar type of thing for the other proposition. So a to the n to the mth power is a to the n times m. So base step is when n is 1, that's a to the first power raised to the mth power, which is the same thing as a to the m, because a to the 1 is defined to be a. So a to the m equals a to, and m is the same thing as 1 times m. So that follows from that. Inductive step, assume that the property holds for some natural number k. And then if we look at a to the k plus 1 raised to the m power, that's a times a to the k raised to the m power. And just using the definition of the powers and stuff, that's equal to a times a to the k multiplied by itself m times. And we can use associativity of multiplication to rearrange things. So we get a multiplied by itself, what is it, m times, and then a to the k multiplied by itself m times. So that's a to the m times a to the k raised to the m power. And then by the inductive hypothesis, a to the k to the m is the same thing as a times a raised to the k m power. All right, and then using the part 1, that's the same thing as a to the m plus km, and then if you factor out the m, you get a to the k plus 1 times m. Okay, so that shows that those rules of exponents follow from follow from mathematical induction. All right, and then just real quick, I want to do number 5. This one's relatively straightforward too. It's done by induction, and like I said, I mentioned this a bunch of times already, but I'll do those other problems in the problem set for chapter 3. All right, so part A says prove by induction on n that the sum of the first n powers of so the first n plus 1 powers of r is equal to 1 minus r to the n plus 1 over 1 minus r, provided that r is not 1, because then you get division by 0. So here 1 you can think of as the 0th power of r, right? So you get n plus 1 terms in that expression. So if r equals 1, the sum certainly presents no problem. That actually he writes that in the book. I didn't say that. That's what he wrote in the book. So proof by induction. The base step is when n is equal to 1. So we get 1 plus r. And if we look at 1 minus r squared over 1 minus r, you get the same thing. So that works out. All right, then for the inductive step, the inductive hypothesis is that the sum of the first n powers of r is equal to that formula for some n. Then consider the sum of the first n plus 1 powers. And if we look at 1 minus r to the n plus 1 over, by inductive hypothesis, the 1 plus r plus dot 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 plus r to the n, that's equal to 1 minus r to the n plus 1 over 1 minus r, and then you just bring along the r to the n plus 1. And that's, if you put both of those things over the LCD, you get the next expression, 1 minus r to the n plus 1 plus r to the n plus 1 minus r to the n plus 2 over 1 minus r is equal to 1 minus r to the n plus 2, because the middle terms cancel out, over 1 minus r. And that proves the formula for all natural numbers. And like I said, this formula here is useful for finding sums of geometric series, which I guess is a topic that we'll go over, later on down the line. Okay, and then in part B, he asks us to derive the result by setting s equal to 1. So we're going to use partial sums. In other words, s is 1 plus r squared, etc., up to r to the n, multiplying this equation by r and solving for the 2 equations for s. So I'm doing that down here. Right, so if s is that sum, if you multiply s by r, you get the sum next to that. So you r plus r squared plus dot 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 up to rn plus r to the n plus 1. And if you take the difference s minus rs, notice that all the middle terms cancel out and you're just on the right hand side and you're just left with 1 minus r to the n plus 1. And if you factor out s from the left hand side, you get s times 1 minus r, and then you just divide by 1 minus r, provided that r is not 1, right? Because you can't divide by 0. And that proves the formula. So that's basically all the problems that I'm going to do in this video. Like I said, let me know if you prefer this format. I did feel like I kind of went a little bit quickly through things here, so I don't know if this is the best way to do it, but it certainly allows me to avoid, mostly typos and mistakes, and it also allows me to cut down on the time for the video. But also, I feel like I went really quickly through this stuff. When I write things down, it does slow me down in my explanations. So I don't know. You guys tell me if you like it this way or if you prefer to do it, see me do it in real time. All right. So I'll see you guys in the next video. What I'm going to do in the Spivak series is for the next video. Actually, let me just stop the screen share for a second. For the Spivak series, the next video will be for the notes for chapter 3, and then I'll do the exercises for chapter 3. And check out my other series on the other books I'm doing as well. I am going through Schifrin's multivariable mathematics. If you haven't had a chance to check those videos out yet, I might try and post the notes for section 1.2 in this book today, if I have time. So we'll see. And then also I'm going through John Taylor's classical mechanics. I haven't posted the videos for this yet, but I should be posting the lecture note, the notes for 1.1 and 1.2 relatively soon, either today or sometime soon this week. So keep an eye out for that. All right, guys. I hope that you are enjoying the content here. I'm certainly enjoying going through these books and these problems. So leave me a comment in the comment section, or and also just a reminder, if you could do me a favor and like and subscribe, that would help the channel grow a lot, because the algorithm takes that into account, and then other people that like this type of stuff can see these videos and as well. So all right, guys, so I'll see you in the next video, and enjoy the rest of your day.